In this video, I'm going to take you through a GoLang implementation of SHA-256. So in this series of videos, and then in this video, I'm going to take you through input and pre-processing. So if we have a look at the overview of how Merkle and Damgard functions work, we have our input and pre-processing, then we have our compression, and then we have our final value construction and output. And so, like I just said, this video is covering the input and pre-processing. We're going to look at input, we're going to look at message block construction, and then the message schedule construction. But before that, we'll just take a look at the specification for SHA-256. So just pulling up the NIST FIPS 180-4 specification for SHA-2. The SHA-256 is in here, but if we just scroll down a little bit, we have just some explanations here, some terms. We have our table of contents. And then here are the SHA-2 algorithms. So this is SHA-1 actually, and then these are the SHA-2 algorithms. So we have 224, 256, 384, 512, 512, 224, and 512, 256. We're concerned with SHA-256. And it also goes through some terms here. So we have what a bit is, what a byte is, what FIPS is, what NIST is, what SHA is, and what a word is, 32, 64 bytes, 4 bits, 4 bytes, 8 bytes. And then just some more definitions here of what's going to be covered. Here we have our bitwise operators. So we have AND, we have OR, we have XOR, we have complement or not. We have addition modulo 2 to the W. So that just means since we're doing this in GoLang and we're using unsigned 32-bit integers, we don't really have to worry about this because it's always going to be constrained to that 32 bits. That's what this addition to modulo is doing. Anytime you do anything to modulo 2 to the whatever that number is, you're constraining that result to however many bits this W is representing. Then we have our left shift operator, and we have our right shift operator, and then we have our rotations, rotation left and rotation right. So in SHA-256, rotation left actually isn't used, so we're going to be using rotation right exclusively. And then we have our shift right. So bit strings and integers, we're looking at bit strings and integers here. It's pretty basic explanation, but basically what this is saying is you can express things in hexadecimal, and this is the corresponding binary or byte code for that. Operations on words, that's just talking about modulo again. And then if we look at the functions, we have our SHA-1 functions here, and then we have our SHA-224 and 256. These are the ones that we're concerned with. We have our choice function, our majority function, and then we have our big sigma 0, big sigma 1, small sigma 0, and small sigma 1. And these are talking about those bitwise functions. We can call them logical functions as well. And so we're just passing input to these, and then these different functions are being performed on that input. So a rotate right, and that means, let's just go back up to where the bits were there. So if we go up here, a rotate right is basically taking this 0 and wrapping it around to the other side of whatever that bit sequence is. So lots of rotate rights. And then we have our XOR here, and then we have our AND here as well. If we go back up, we can have a look at what those definitions were. So this is our bitwise AND, and then our bitwise XOR, and we'll just jump back down here. So when we have an AND, what that means is, like, if we wanted to add these 4 sets of bits together, an AND would mean both of these need to be 1 in order for that result to be a 1. So this would be a 0, this would be a 0, this would be a 1, and this would be a 0. And then an exclusive OR would be, it means that one of these has to be a 1, not both of them can be a 1, and then 0 is obviously 0. So if we were exclusive ORing these two sets of bits together, this would be a 1, this would be a 0, this would be a 0, and this would be a 1. So then the next part is the constant values. So SHA, or the specification, provides these. SHA-256 uses these constant values, and so where they come from they're the fractional portion of the first 64 prime numbers. So it's the cube root for these constant values. So you take the cube root of each of the first 64 prime numbers, and then you take the first 32 bits of the fractional portion of those numbers. So the numbers after the decimal place, you take the first 32 bits of the numbers after the decimal place. And that's where these come from. But they're already specified, so you don't really have to worry about that. That's for the other functions. So the example input they're using is ABC, and our testing input is going to use that example input as well. Continue on here, and so here are our initial values as well. And so these initial values, instead of coming from the cube root, they're actually coming from the square root. So it's the square root of the first 8 prime numbers, and then you take the fractional portion, first 32 bits after the decimal place. And if we're just continue jumping through here until we get to the pseudocode for SHA-256, here we go. And so here are the steps. So we have the pre-processing steps, and what we're doing here is we're preparing the message blocks. And how message blocks work is they're split up into 512 bits. And so you take your input, and then you have to pad your input in order to get it to a size that's 448 bits congruent to 512 bits. I'll take you through the code to show you exactly what that looks like. But then once you have your message blocks, then you take those message blocks and you split them into message schedules, and you feed those message schedules into the compression function of the hash function. Then you compress it, and then you take your final values and you concatenate those final values and put them out to output. And so that covers basically the NIST specification. So now let's jump into the code and have a look through that. So opening up my terminal here, the way I'm going to do this is I've just split the pane in tmux, so 2 panes. I'll run a couple of test functions just to show you what the output is looking like, and then on the left hand side here I'll just go through the code. So jumping into the main file here, we have our main function, and in our main function what I've done here is I've just added a couple different options in order to input strings to this program. So it is a command line program, but there's a couple different ways you can pass it input. Usually most hashing function programs like OpenSSL, for example, you don't actually pass things directly to it. You usually pipe things to it. So for example, we can go echo and then truncate the new line character at the end of it, and we'll just say test. We would pipe that into OpenSSL, and we can say SHA-256. And that'll give us an output. So that's different from saying OpenSSL SHA-256 test. It doesn't accept that, but our program will. So we'll be able to do it in both ways. So that's basically what this is doing. We have our inputs here, and then once we get our inputs, we are passing that to this getHash function. And so the getHash function is converting our input message to bytes. And interesting thing about GoLang is it actually treats runes or characters as bytes anyways. So these are really easy to convert, so you can just cast it or convert it from an input string to bytes. And then from there, we are creating our message blocks. So this is the first file in our pre-processing package. So we can just do a jump to definition. We'll jump into this message block class. And so what's happening here is we're having that message, that byte message passed to this function. And then we're creating a new blank byte array so that we don't corrupt our message. And what we're doing is we're appending our message first. So those bytes, and I'll just quickly show you if we do echo -n ABC, and then we can do XXD and pass it the binary flag. That is what ABC looks like in binary. So that's A, that's B, and that's C. And so that's what's being passed into this function here. And then we're adding that to our array of bytes. And then the next thing we need to do is add the 0 padding bits, just like the NIST specification. So to do that, first what we need to do is we need to add a separator bit. And then we add the necessary padding, because we already have our message added to that array. And then we add our separator bit, and then we add the necessary padding to get our message block 448 bits congruent to 512 bits. And I'll just show you, if we go test, we can do pre-processing, and we'll do a message block test. We run that. Oh, we need to do verbose. There we go. So now we have our blank array. Here's our ABC. And now here's ABC with the separator bit. And then our padding zeros up to 448 bits congruent to 512. And so how did we do that? Let's get down to how much padding. And so how we're doing that is we're calculating our message length. So it's 24 because it's 3 bytes. 3 times 4 is 24. But then to figure out how much padding we need, we use the modulus operator. So we say our message length modulus 64 because 512 bits is 64 bytes. And if that remainder is less than 56, we know that it's only 1 block long, or 2, depending on how long the input message is. But anyways, it's just congruent to. It has to be 64 bits shy of a multiple of 512 bits. But anyways, for our purposes right now, because we're using the input ABC, it's only going to be 1 block long. So if that's the case, it's going to be 56 minus our message length modulus 64. Otherwise, if it was bigger and we needed more blocks, or it was not quite flush on however many blocks because of the message input size, we would go 64 plus 56 minus message length modulus 64. And that tells us how many zeros we need to add. So we have our separator bit, and then how many zeros we need to add to get to that congruence. And then once we have that, the last step is we need to add our message length. And so we know that we have 3 bytes in our message. So our message is 3 bytes long, and we know that there are 8 bits in a byte. So we know that number is going to be 24. And the way that we add that is we say, we just make another quick byte array here, and that's going to be 8. And then we just use the binary package in the big endian class because SHA-256 uses all big endian values. RipeMD160 uses some little endian, but SHA-256, all the SHA-2 functions use exclusively big endian values. So we just put that message length on the end of our message block. We append it, and that's what this is here. So it's these last 8 bytes here. So it would be 1, 2, 3, 4, 5, 6, 7, 8. And that corresponds to 64 bits because 8 times 8 is 64. And that's in big endian. So this is the number 24. And those are the rest of those bytes. And that gives us our message block. So we have our message block. And the next step is we need to get our message schedule. And so the way this works is we get our message block, and our message block is a multiple of 512 bits. And so it could be one message block, or it could be a bunch of message blocks. And 512 bits is 64 bytes. And so what this loop is doing is it's just going to loop through all of the available message blocks. And then for each of them, it's going to split out the 512 bits. And then it's going to create a message schedule. So if we do another jump to definition, we'll jump into our message schedule class. And what's happening here is we're taking our message block as input now, and we're creating our schedule. So according to this specification, how this is working is we take our first 16 words from our message block. So 64 bytes that splits out into 16 32-bit words. So all of these are going to be our initial 16 words. And then to get the remaining 48 words, because we have a 64-word schedule, we use this process right here. So this is getting our first 16 words, and then to get our remaining 48 words, we have to get them using logical functions specified in the NIST specification. If we pull the specification back up and we just have a quick look at this here, so we have preparing the message schedule, we have our first 16 words, and then for the remaining 48 words, we're using this process. So we have small sigma 1, and that's being passed word t-2 plus word 1-7 plus small sigma 0, t-15 plus t-16. So let's take a look at what that looks like in the code. So just jumping down to this function here, we have our logical function. So small sigma 1, and for this first word here, so it's I is 16, so I minus 2, this would be index 14, which would be the 15th word, or the 13th word, sorry. And let's just have a quick look at that. We'll do a jump to definition. And so that's being passed in, and then we're getting a rotate. It says left here, but it's actually rotate right. GoLang doesn't support a rotate right, but it does a rotate left. But if you pass a negative number to that rotate left, you get a rotate right. So we're doing a rotate right by 17. This is probably a little bit more clear. And then we're XORing that with a rotate right by 19, and then XORing that with a shift right by 10. And so the difference between rotate and shift, rotate, you're not losing information, you're just rotating it around to the other side, versus a shift, which doesn't care if those bits get shifted off the right part of the byte of the integer, it just gets rid of them. So this is one way you can lose data. In the first chapter we talked about the difference between hashing and encryption. This is a major one. And so this is a big reason why these functions are pre-image resistant, because you're losing that data, you're losing that information when you do this. And so we do small sigma 1 plus the schedule of I minus 7, and then small sigma 0, jump to definition on this one. Same kind of deal here. We're doing a rotate 7, XORing with a rotate 18, and then XORing that with a shift 3. And then we're adding that to I minus 16. And so we do that, we run through this, and we get our 48 word schedule. And so let's just pull up a test on this. We'll go test for both this time, pre-processing, and we'll go pre-processing message schedule test, but we're going to need to add a dependency to this one, so we'll also go pre-processing, and we'll go message blocks, and we'll run that, and there is our message schedule. And so we have our values here. Here's our block again, and then here's our schedule. So we have our initial value, and this is in hexadecimal instead of binary, just to confuse you. No, I'm just kidding. But you'll see here's our message schedule, and this is our 64 word message schedule. So we have our first 16 words here. You'll see the zeros that corresponds to our message block, and then the rest of those words are built using this process. And so that covers the input and pre-processing more or less. So we have our message blocks, and then we take each of those 512-bit or 64-byte message blocks, and we turn them into a message schedule. And in the next video, we're going to cover the compression part, where we take each of our message schedules and we pass them one by one to our compression function for them to be compressed, and then they get returned as chaining variables if there's more than one message schedule that needs to be compressed. But using our input ABC, we're only going to have one, so that becomes our output value, which we'll cover in the last video of this series. So I'll see you in the next video.